Okay, so today's agenda is, as you can see on the screen, I will have a short presentation of EPMA and its activities. And then we have two speakers. The first one is Klaus Almundkop from Fraunhofer IFAM Bremen. He is the group leader of additive manufacturing in the institute. And also he is the chair, one of the chairs of our sectoral group of additive manufacturing Euro AM. And then we have Walid Frika, who is the sales manager of Granatools from Belgium. Granatools is, as you may know, is a company specialized on measurements and metering in powder metallurgy. So regarding EPMAs, so for the ones who have no idea about what EPMA is, I will go step by step. EPMA is the European Powder Metallurgy Association. It is a non-profit association established in Brussels in 1989 with three key missions. The first one is promoting and developing PM technology in Europe and representing the PM industry in Europe, either international or around the Euro land, and develop the future of powder metallurgy. The best definition I would like to express is the one that writes underlined as below. EPMA is what its members want it to be. So regarding the history of powder metallurgy, if we make a schematic explanation, we can consider as a tree where the roots are our materials, that is the ferrous and non-ferrous alloys, the hard materials, tungsten carbide, and together with cobalt interfaces. So with all these materials, we will build up our applications. So the very first one and the basic one of powder metallurgy application is present sinter. It is one of the main applications used in automotive steel. And then we have the second sectoral group, let's say, or the application, which is the hard materials, especially for cutting tools. And then we have metal injection molding. And also step by step, as you can see, new applications has been evolved. EPMA have contracted new sectoral groups to represent these industries. So as new needs evolve with new projects, lobbying and networking, and as new processes develop with using some maybe new materials, new sectors are born. So in the end, maybe we will have a seventh sectoral group within the next 5 or 6 years, we don't know. Regarding the EPMA sectoral groups, as you can see, we have 6 sectoral groups, and what they do, okay, these sectoral groups have regular meetings to follow up the industry and together with university and academicians. Also, we have the statistical service to collect data about powder metallurgy in Europe. And then we also have the benchmarking service to give an idea about the current situation and the future of the industry, together with the trend service and the benchmarking service. And then, of course, we have the seminars, as you may already know, depending on each sectoral group, we organize seminars regularly. And we also have publications. As you can see, we have 4 booklets for additive manufacturing, hipping, MIM, and present sinter. We are working on the preparation of the booklets for AGEM and functional materials. I think by the end of the year, we will have the complete set of brochures for each of our sectoral groups. So I also want to say some words about the working groups of EPMA. We have 2 main working groups. These are EHQS and EPMI. EHQS is the working group of EPMA on environment, health, quality, and safety. It has three subgroups, as you can see on the screen. One is ISO and standardization. The other one is chemical management, about regulations and legislative issues. And also a subgroup on life cycle analysis. EPMI is the European Powder Metallurgy Institute, what we call as a kind of a group of academicians coming together from the research centers and universities, and they work on development of projects. They work on transfer of students or staff in between, and also they support EPMA with respect to education and research topics to promote powder metallurgy on the Euroland. Okay, for the EHQS working group, I would like to invite you to join our, let's say, bi-monthly newsletter, follow up the issues related with powder metallurgy, as it looks like standardization and chemical management will be one of the important topics for powder metallurgy within the next years. So, regarding the European Additive Manufacturing Group, the EuroAM, as you have seen it on the tree, it was set up in May 2013, together with the companies and organizations in the supply chain and who are members of EPMA. It is one of the most active groups in EPMA. As EuroAM, we organize seminars regularly every year. For example, last year, the seminar was in Gothenburg, Sweden. Unfortunately, this year, we had to postpone it to December. It was planned to be in Augsburg, Germany, together with Fraunhofer IGCV. I hope we will be able to realize it in December, and you are kindly invited to attend this seminar. And also regarding the publication of our brochure on additive manufacturing, we announced the third edition of this booklet. It is one of the main handbooks of additive manufacturing. You can download it freely from our website. And also regarding the statistics in AM, EPMA's statistics, especially the trans service, is one of the main statistics followed by the whole industry. But it is unfortunately available only to members and participants of the survey. So I want to say some words about EPMA's club projects. Okay, the club projects are the projects coordinated by EPMA based on the ideas coming from universities and R&D centers, or what we call the contractors. We announced these project ideas to the industry to find some partners who will fund the project. Up to now, we have completed 28 club projects as EPMA, and we raised more than 1 million euros for these projects from the industry. Currently, we have 6 projects running, and we will have 3 more projects to be started before the end of 2020. The next thing I would like to mention is the EU-funded projects of EPMA. Up to now, EPMA has been participating in many different EU-funded projects, and these are namely AM Motion, EFIC Pro, and the current running ones, especially Supreme and SAM. These are all projects within the scope of Horizon 2020 or either Mercury in training networks. I want to say some words especially about sorry. Yeah. Okay. I'm sorry. Okay, so regarding the SAM projects, I want to say some words about our invitation to join its LinkedIn groups, especially for the students, trainees, and job seekers in additive manufacturing. You're kindly invited to join SAM projects LinkedIn groups that you can make a good benefit of networking within the European additive manufacturing industry. So the most important thing I would like to mention is the European Congress 2020. It will be held online this year due to COVID-19 case for the first time in the history of EPMA. It will be a 3-day event with more than 150 presentations, so it will be a very tight program. So the technical program will include the presentations on technical sessions, the special interest seminars, and we will also have a plenary session where our president and our executive director will make good presentations on the industry itself, on powder metallurgy and other issues. You can follow the event or join for registration or other issues from the website european2020.com. So thank you for listening to me. That's all I would like to say. Now I think it is time for me to leave the ground back to our speakers. So our first speaker is Klaus Amundkopf. So Klaus, are you ready?
I'm ready, yes.
Okay, so here we go on with our first presentation from Klaus. As I said, Klaus is one of our chairs in EuroAM sectoral group. Now he will make a short presentation about the outlines of additive manufacturing based upon the book they have prepared together with Adel and Ryu. So the floor is yours, Klaus.
Okay, thank you. Can you hear me, Kenan?
Yes, you can. Yes,
okay,
we hear you well. Go on, please. Yeah.
The first thing, I shared my screen already. Is it visible? Should be the title slide. Okay.
Yes,
so
yes. You're ready.
Everything seems to be well prepared. Thank you for that.
You're welcome.
Let's start with some outlines of additive manufacturing. Most of the information I'm talking about during the next 30 minutes is taken from the brochure Kenan has already mentioned, which can be downloaded for free on the EPMA website. So please have a look at this brochure, load it down, and read more thoroughly through the topics than I will be able to present. So, introducing additive manufacturing. AM, as it is mostly called these days, is also known as 3D printing, or in former days it was called rapid prototyping. It's also called freeform fabrication, but it's all about a process of joining materials to make objects from 3D model data. Usually this is done layer by layer, so opposed to subtractive manufacturing technologies like milling and other machining technologies. You simply add material to your product. And as we are within the EPMA, I will be talking about the metal powder-based AM processes during the next couple of minutes. The special thing of AM is simply that you have a very wide horizon concerning your freedom of design. You may see this at objects like these, made by some artists and then printed by companies like nowadays Digital Metal, or you can print things like these cups with integrated structures. This was printed by Arcom in this case. So AM has definitely special benefits. I already mentioned this increased freedom of design. You can build very lightweight structures like displayed here on the right. You can add additional functionality to your products like internal channels, which can only hardly be casted or drilled into your products. You have less raw material consumption, sometimes up to 25 times less versus machining. If you mill away, let's say 90% or even more of an aluminium block, this is not the case with AM. You only use the material where you need it for your product itself or for certain support structures. You do not need tooling. You directly print from the 3D model. And in most cases, you have very short production cycle times and can also, and even complex parts, produce in a few days. And in many cases, much faster than with conventional machining. Of course, as with every technology, there are limits, also with AM. One of the limits is the part size. So at the moment, we are ending with the machine size as of 800 by 500 by 400 millimeters, which is one of the very big laser melting machines. A binder jetting machine of the same size is announced, but having such a machine does not always mean you can print these big parts. So you are definitely limited in part size. Part design is also limited to some extent. If you think of support structures you need, especially with laser-based processes where you build on platforms. You have overhangs with some products which have to be supported and things like these. Concerning the size of production series, additive manufacturing is still seen as being limited to, let's say, lot sizes of, here it says 25,000. We have seen products which are produced to 100,000 a year, but compared to mass production, AM is still limited to smaller lot sizes due to its flexibility. It doesn't make sense to produce mass products like screws or things like these. Material choice is another topic which is still limited to some extent. Meanwhile, we have a lot of alloys around with the different processes. Here it still says non-weldable materials cannot be processed by additive. This is limited to the laser beam melting process. If you look at metal binder jetting, there you can process all metals. You can also sinter. So you can, or you have always to have a closer look at your product, what you need and which product and process is the right one for your product. The part properties from time to time still suffer from porosity. This is also process specific. In most cases, we have a statistically distributed porosity, which is common to classical powder metallurgy parts. So in this respect, we are only limited to a very small extent, and we are very well and very close to classical metal parts which are produced conventionally concerning the part properties. So having an overview on the different processes, mentioned before, powder bed fusion technologies like the laser bed or laser-based LPBF, which is laser powder bed fusion. This is also possible with an electron beam as an energy source. Then it's electron beam powder bed fusion. And relatively new, having come back from 20 years ago, is the binder jetting approach, where a liquid binder is printed into the powder bed. Details will follow. And on the second arch, we are looking at the directed energy deposition, DED, processes where we have energy sources as lasers, EBs, and arcs, and feedstocks like wire or powder. So this can be a general overview over the different processes. Looking at the powder bed fusion systems, the most and widespread processes are the laser beam powder bed fusion and electron beam powder bed fusion, which work more or less the same way. So a powder layer is applied on a building platform, and then the laser or electron beam selectively melts the upper layer of the powder. And this is also standardized in the according standard, and there it's called additive manufacturing process, in which a thermal energy selectively fuses region of a powder bed. These melting processes are repeated layer by layer, and in this way, in most cases, by lowering the platform, the 3D product is built up in the building chamber. Going into a bit more detail concerning this process, a typical AM machine based on a laser as an energy source has a stationary laser gun, and the laser beam is then controlled by moving a mirror. So the whole surface of the building chamber or of the building platform is scanned by this laser beam to the position where later on product volume shall come into existence. The first machines had only one laser. Meanwhile, we have machines with double lasers and even with 4 lasers integrated into the system, simply to be able to scan larger building platforms and to speed up the production time. Recycling, a very important aspect, is possible. Recycling of the used powder, not of the one being built into the product, but of the powder which is still surrounding the completed product in the end. This powder can be sieved and re-sieved, and in some cases been mixed with virgin powder, and thus it can be reused for the next process, for the next build job, at least to a certain percentage. Another detail of the laser melting process, you see the beam scanning into this direction and melting the loose powder, and here it still says laser sintering. This is not the correct term, as it is no sintering process, it's a melting process. And so by moving on into this direction, the beam melts up the powder, and in the end you have a completed product. And the physics behind this is partly absorption, partly reflection, partly scattering. So a very complex process in detail, but it's state of the art today. And we have laser powers between 200 watts and 1,000 watts, meanwhile being able to melt the metal powder and build up complete metallic products. Electron beam melting is a bit. It takes place under vacuum. That's the first big difference. and it has an electron beam instead of a laser beam as an energy source. The laser process takes place under protective gas, mostly nitrogen or argon, depending on the material used. As said, EBM does the same in vacuum. It's necessary for the electron beam to be scannable in the end. And another special thing with EBM is that every powder layer is preheated before it's melted. And this preheating results in a hot process compared to laser melting. And the big advantage of EBM, therefore, is that we have very, very low or almost freedom from residual stresses. And therefore, EBM is used for very special materials in the end, and has found its way into the market next to the laser beam variant of more or less the same powder bed based process. A newcomer or a revival, a renaissance is allocated to the metal binder jetting plus sintering process, which has seen a renaissance from the late 1990s, where this technology had come up already, but nobody was interested in it due to the lack of the overall additive hype. Now it's back for some years already, and the metal binder jetting process is something completely different compared to the beam-based technologies. There we do not have a beam melting powder, we simply have a printer printing a kind of binder. Here it's a liquid bonding agent in the standard, and this liquid bonding agent is selectively deposited to join powder materials. So no metal powder melted together, but in a first step bonded together. It's also a powder bed based process. So you're preparing a powder layer, the print head comes and prints binder into the powder bed. Then you have a small drying of the binder in between, and then you repeat these steps 1, 2, 3. So powder layer, printing binder, drying, and then you end up with so-called green parts. As we know this from standard powder metallurgy, you end up with green parts being printed. These green parts, together with the whole building blocks, are then cured in a furnace, and then you can remove these green parts out of the powder bed. You can also reuse the powder to a certain extent, and then you take these green parts into a debinding plus sintering step, and depending on the technology and on the material you use, this debinding plus sintering can take place in one step, in one oven, and this is really meant the parts become smaller, as with classically sintered part, so you have the classical shrinkage from binder jetting is sorry, Kenan, can you just tell me if I'm still?
Yes, we hear
track?
you, and the presentation on the screen, as far as I see. Yes, you can go on.
Okay, that's fine, because I lost
yes, there was
my
a
audio
small,
connection.
a little cut on your voice, but now it's back. It's fine. You can go on. Okay, please.
Okay, thank you. So some facts about metal binder jetting plus the subsequent sintering step. Metal binder is assumed to be much faster than the powder bed fusion processes mentioned before. Costs are assumed to be lower. We do not have reliable figures yet, but we are on a way to establish binder jetting as one of the processes into industry, one of the metal powder-based processes. And one of the biggest advantages of metal binder jetting compared to EBM and LBM, or powder bed fusion processes, is that you do not need supports, at least not during the printing step. And the build box can be completely filled. And if you look at build box sizes of this size, 800 by 500 by 400 millimeters, you have much more volume during one print job to be filled. That's at least assumed. Of course, you need two process steps, printing plus debinding and sintering, but for the powder bed fusion processes, mostly also thermal treatment is necessary after the printing step. You have green parts to be handled in the end. These green parts are brittle, so green part handling in between the two process steps is still a challenge to some extent. You are a bit limited concerning the wall thicknesses. So if you want to have very thin walls, the beam-based technology, especially laser beam melting, might be a bit more advantage compared to binder jetting. Concerning the materials for binder jetting, we have all materials which can be sintered in the end. One exception today might be aluminum, which is still missing here for binder jetting, as sintering of aluminum is a very special thing and a science on its own. Only a very few companies are able to do that. So aluminum for binder jetting is not state of the art today. Coming to the third process group, which is directed energy deposition, and some people say this is not a real AM process as it's not layer by layer. If you see it very strictly, but DED is part of the market, definitely, and powder is used for the process. So you have a powder feed here and a laser melting the powder, and then you have a welding process, a clear welding process. And if you use a 3 or 5 axis manipulating system, you can end up with very large and very complex structures. A limit with DED is the production of very small, very fine lattice structures or internal channels. There, DED is definitely limited compared to the other processes mentioned before. If you look at the main process steps in AM, you have all the same with the different processes. You start with the 3D modeling. You take a 3D model, you take a 3D scan, so a reverse engineered model, which is then transferred into the so-called stereolithography data, which is or has become the standard data for additive manufacturing. So STL data is triangulated surface data. This data of the model is then prepared, so pre-processing for the printing step itself. Holes can be repaired, the surfaces can be turned, the part orientation is defined, so the positioning in the build chamber is defined, and then this model data is sliced, so cut into slices, so it can be printed layer by layer for most processes. This data preparation step, meanwhile, is supported by lots of different software solutions, very sophisticated software supports. Support is the right keyword. This software, to some extent, allows an automated positioning of support structures for the beam-based processes, for example. And the third step is the manufacturing on the AM machine itself. There you create machine data and you produce the parts. This is the real printing step, the real 3D printing step. And in the end, you have, depending on your process and on your material, you have post-processing steps like powder removal, support structure removal, build platform cutoff. You have a heat treatment with most processes, and surface finish and polishing, etc. Lacquering and all things you can do with conventionally produced metal parts too. Again, post-processing, so powder removal, support, base plate, heat treatment, machining, surface, as said before. One special thing is the hipping, and hipping means hot isostatic pressing, which is still done with a lot of 3D printed products. As I mentioned at the very start of this presentation, we have in many processes a certain amount of statistically distributed closed porosity, and with closed porosity, hipping would be the right post-processing step to get rid of that. Open porosity at the surface can't be solved with hipping, of course, but hipping is used by very many manufacturers, therefore it's mentioned here. Okay, one big topic concerning additive is always the keyword topology optimization. Topology optimization, well known by many of you, I think. There you have software which allocates material only there where it's really necessary for the purpose of the part, mechanical loads or other things the part shall fulfill. And these complex structures can be printed with most of the 3D printing processes. So topology optimization has become more reliable, or has become more common with 3D printing. So 3D printing has become a real enabler of topology optimized parts. And this is one example. It's a bracket or something as taken from a satellite design and therefore low weight, very stable, but complex geometry, ideal for being 3D printed. Standardization in AM is one big challenge still. AM in general is a relatively new technology compared to, let's say, casting, which humans do for more than 5 or even 10,000 years now. So standards in AM are still needed. A lot standards are still needed, and standardization is a hard business, time consuming. Nobody pays for it, but a lot of colleagues are involved in standardization, even in AM. And in the US, it's the F42 technical committee who does standardization for more than 10 years now, especially for AM. And meanwhile, we have an ISO committee, which is the TC 261. And A lot of national standardization bodies are taking part in these international standardization activities. So there is a lot of work ongoing, and it's not only ISO and ASTM. A lot of national standardization activities are ongoing. In Germany, I can talk for the VDI, the Association of German Engineers, who's come up with a lot of guidelines, which perhaps later on are transferred into standards and even international standards. And my appeal for everybody can only be engage yourself into standardization activities as far as you can. They are needed to bring the AM technology forward, and it's up to everybody, him or herself, to engage into this. Another overview, market perspectives of AM. Well, everybody is talking of the new possibilities. You have this freedom of design. You have, in some cases, new materials. You have things like topology optimization and things like that. And therefore, aerospace, as well as tooling industry, automotive industry, and medical industry or life science in general, are looking into the new possibilities they gain with additive manufacturing. And it's up to you and your companies to find the right products for 3D printing processes and applications, or use or take old products and integrate new functionalities. And this is the key word. Last but not least, we have this. We have a lot of case studies also in our brochure. Just some examples over here. So you can realize and design internally cooled bone drills, or drills in general. So internal channels is a big topic. You can use AM for processes which have been casting processes with a lot of process steps, and here the material was cobalt chrome. So dental industry has taken a deep insight into additive manufacturing, and many dental parts are 3D printed meanwhile. We have things like complex tools with internal lattice structures, with internal cooling channels, very sophisticated designs where 20 parts have been converted into one printed part, for example. Brackets like these are topology optimized things. We've spoken about that. This is a very nice example made from a nickel-based alloy. So for high temperature application, it's a ball joint, two walls somehow connected to another element, and rotation up to plus minus 10 degrees is possible. And here the very last one is again a steering knuckle made from an aluminum alloy. And yeah, this one is also topology optimized, and we have integrated functions, and we have 40% less material compared to the conventional, the machined variant. So this was a fast and very basic overview on what AM is capable of. We have a lot of new possibility with these processes, and it's up to you to find the right product and to improve these processes. Thank you very much for your attention. I have one slide on my own behalf. If you want to dig deeper into the sinter-based AM processes like metal binder jetting or fused filament fabrication, which was not mentioned here, join us for our Fraunhofer workshop at IFAM next February. And yeah, thank you again for listening. Kenan, it's up to you to introduce the next speaker. Thank you.
Thank you very much, Klaus. This was really a nice and compact presentation to describe everything to beginners in AM, let's say. And that was our goal, actually, in this webinar. Now, we will go somehow in depth with some technical details in our next presentation, where Walid will make a nice presentation about powder metallurgy, measurement tricks and issues like that in additive manufacturing. So, Walid, are you online? Can you hear me?
Yes, I am. Can you hear me too?
Yes, I can hear you. Maybe you can share your screen. Oh, yes. Now, as I said, Walid is from Grana Tools. Grana Tools is a company based in Belgium, mainly activities in measurement of powder flow and other details. Now the floor is yours, Walid. Have your presentation, and after then, I'm sure you will have a lot of questions depending on your presentation. Okay, thank you.
Thank you for the introduction. So, yeah, this presentation will focus mostly on powder characterization for additive manufacturing. And as said during the introduction, one of the challenges of additive manufacturing is the layers. So the goal is to understand how the powder will spread into layers. And we can see that this is the general slide that we are using to introduce powder characterization, because powder characterization is an issue in several industries, the additive manufacturing being one of them. So what we want to understand when we characterize powder is the collective behavior of the powders. So we want to understand how it will spread, because this is the main topic we will discuss today. And the spreading of a powder will depend on two things. The first one is the particle, so the grain properties, and the second thing is the interaction between the particle. And if you could somehow compute those data together, you will be able to understand the collective behavior. Unfortunately, today it is not as easy. This blue arrow is way more complicated than it looks. So we are characterizing powder in several ways. We can characterize the grain properties with measurement like PSD that we are all very familiar with. But in Grana Tools, we are physicists. So we focus mostly on the forces acting on the grains. And the forces we focus on are the cohesive forces. So what is the cohesive forces? It's the sum of all the forces that are short-ranged and attractive. So this is the forces that will make the particle stick one to each other. And if you take granulated sugar or flour, you can see that the flow properties of those two powders are different. And the reason is different is because those some particles are sticking more than others. So the cohesive forces, there is three cohesive forces: the van der Waals forces, which is due to chemicals, so you cannot do much about it; the electrostatic forces that can build up in some process, so it is quite an important topic; and the capillary forces, which are due to humidity inside the powder. So this is what we want to characterize, is the cohesive forces, and we can assume that if the cohesive forces are low, then the powder will flow well and therefore spread well, and if they are high, then they will not flow that well and so not spread that well. The thing is, during the introduction, we told you that I work for Grana Tools, which is an equipment manufacturer that produces several equipment, and the question I always get is, why do you have so many equipment to characterize the cohesive forces? And this is the second principle about powder characterization. The measurement device works as a proxy for the process condition. When you want to characterize a powder for a process, you need to understand what are the process conditions. And specifically, you need to understand the stress state that you can see here on the y-axis and the flow fields on the x-axis. If I want to understand the powder behavior inside an industrial silo, I need to characterize the cohesive forces. But in the silo, we have very high stress states and very low flow fields. This means the powder is under a huge amount of stress and it's barely not moving. So you need to find an instrument that will reproduce those process conditions, like a shear cell, for example, when you need to put pressure on the powder and to move very, very slowly. Now, what we will focus on today is spreadability, and the spreadability is done with a 3D printer recoater. And in the case of a 3D printer recoater, you need high flow fields because the goal is to recoat as fast as possible. The faster you recoat, the faster the piece will be printed, and to have almost no stress state because the powder is at atmosphere pressure or even lower depending on the process. So the goal is to find an instrument that will mimic those process conditions. And in our instrument at Granule Tools, we are using the Granule drum. So it's a rotating drum principle to do this kind of measurement. So I will just spend a few minutes on explaining what we are actually measuring with a rotating drum principle. So here you can see two videos. This is two rotating drum rotating at the exact same speed. So the speed is the same. And on the left side, you can see a non-cohesive powder. So this means the particles are not sticking one to each other. The cohesive forces are very low on the powder on the left. It's glass beads for your information. On the right, the cohesion is higher. And so we can see that the flow is not as regular. On the left video, the blue video, when the drum is rotating, if the grain is too high regarding the flowing angle of the powder, it will just detach itself from the powder and flow, creating a flow inside the drum, which will make a very, very constant interface. The interface is barely not moving. On the right side, when the grain reaches a height that is too high, it cannot flow on its own because it's sticking to the rest of the powder, so it cannot fall freely. It needs to wait to have enough powder for it to fall, so it will reach a critical mass, and the amount of powder needed to detach one block of powder will depend on the forces that are let's say, connecting the grains one to each other. So if the powder is highly cohesive, it will need a lot of mass to break. And if it's not cohesive, each grain can break separately and create a flow. And what we are doing with this rotating drum principle is to measure the temporal fluctuation. So what is the temporal fluctuation? Is the amount of fluctuation in the powder beds versus the time. So we take a picture of the blue video every second for 30 seconds. So we have 30 pictures and we compare those 30 pictures one to each other. And then we'll do the same with the red video and we will see what is the deviation of the average angle. So I will just give you the final result directly. What you can see in red is the average interface. So this is the average one. And what you can see in green are the maximum and the minimum. So the maximum and the minimum are a specific formula, is the least square meter, but basically it's maximum and minimum. And the area between the maximum and the minimum is one of the parameters to measure the cohesive index. And so we can measure a cohesive index at each speed. So I can tell you that for this powder, which is flour, the cohesive index at 2 RPM is 42.8. This is my value. And from experience, I can tell you 42.8 is not good. If you want to use a powder in an additive manufacturing process, you need to be between 10 and 20, depending on your geometry, the geometry of your machine and your recoater. But yeah, between 10 and 20 is a good value. Glass beads are under 10. Made starch is above 80. So we have, let's say, a table of value depending on the material. And what we can see is that the cohesive index is a function of the rotating speed. So if you measure the cohesive index at 2 RPM or at 20 RPM, you are not getting the same value, which is logical because the goal of the characterization, what we wanted to comply to is the process condition. Depending on the speed of your recoater, you will not gain the same spreadability. Depending on the speed of the rotating drum, you will not get the same cohesive index. So this is something that is very reassuring because we can tune the speed of the rotating drum for it to match the recoater speed and have a very close proxy to the process. And we can see on this slide that the cohesive index in the y-axis is changing depending on the rotation speed here on the x-axis. We have two powder. It's still both, but one is virgin, the other one is used one. And the question was, can I use the used powder seamlessly with the virgin powder? So what we can notice is that the cohesive index depends on the speed, and at low speed, the used powder has a better cohesive index than the new powder. This is because when you put a powder inside the machine, there is some filter, so we are losing the fines, and if there is less fine, there is less contact ratio, so the cohesive index is getting better. But if we go at high speed, there is other effects, like for example, the carbon content in the powder is a bit different, and so the cohesive index is not the same. And so if you want to spread virgin powder and used powder seamlessly, then you should work at a speed which is about 40 RPM. And for this, in Granule Tools, we have a table that can connect the recoater speed and the rotating speed, so you can find, let's say, the approximative speed that you should choose for this process, at least for this powder. So this is how we do the measurement. Now I will explain you a little bit more with examples and more data, let's say scientific data. Just the first thing I want to say is all the graph I've showed you, or I will show you in that presentation, are available online on www.granultools.com. So if you want more information and more precision, please go online into the reference tab and you can download the application note, and then you will have all the information. Here I will just present the main points, of course. So now I will focus on the rotating drum principle. I explain you that the rotating drum can help us measure the cohesive index, that the cohesive index is measured with the temporal fluctuation of the powder interface, and that this will depend on the speed. So we choose 4 titanium powder that I use in the medical industry. This is used to print implants for people who break their skull or their bones. And we wanted to characterize the cohesive index on those powder. So what we do on the left side, you have 2 pictures. So this is a test bench. And you can see that the picture A is not having such a good powder layer. So there is some wave, there is some irregularities, which could lead to a bad final part. So this is what we don't want here. On the bottom, we have a very homogeneous powder layer, which will lead, we hope, to a good piece. So this is what we want. And we run those 4 powders on the granule drum. And what we can see is that 2 powders, the blue and the green one, had a cohesive index which is between 15 and 20. Which are generally good value, let's say. And the 2 other titanium powder had cohesive index, let's say, between 35 and 45, which are not so good value, let's say. So what we can do with this test bench is to run several powders on it, assess the powder bed quality with the eyes, and then decide to put a threshold. And here the threshold was set at 24. So this means that every time you want to print a powder, I mean, here is not a printer, it's a test bench, but every time you want to put a powder inside the test bench and know in advance if the powder layer will be homogeneous or if the powder layer will have irregularities, you can just use the granule drum. And if the cohesive index is below 24, then this means it will spread evenly. If it's above 24, you may have waves or minor irregularities. So this is what we call the pass-fail test. This is used for quality control. You can characterize your powder to understand what will be the homogeneous powder layer. Now we wanted to go one step further and use this method in the real printer to make sure that measuring the temporal fluctuation of a powder bed is a good way to characterize spreadability. So here we can see a good regular layer inside an SLM printer, and here you can see an irregular layer inside an SLM printer, and we can see that it's very easy with our naked eyes to make the difference. But the goal is not to make to see such a big difference. Our goal is to notice the very small difference, to really make to really be able to sort several powders that are on the same grade. So what we want for that is to improve this naked eyes system and to create a way to assess the powder with a machine and to compare the cohesive index and the powder bed irregularities with a machine. So we started a new set of experiments with 3 powder. So there is, I'm not sure it's an inconel, I think it's a scalmalloy, a titanium powder, and aluminum alloy here, so 3 different powders. And what we do is inside the printer, we are taking picture from the top. So we can see that at 30 millimeters per second, we have a quite regular powder layer. At 80 millimeters per second, we start to have small waves. And at 160 millimeters per second, we have irregularities and we have big waves. And so we put those 3 pictures inside a software that we call the granulator. And the granulator is giving us the interface fluctuation of the powder. So do not pay attention to the layer numbers, it's not an important parameter. But what we can see is we have the interface fluctuation of the powder bed. And we can see that for the scalmalloy, it's low at 30 millimeters per second, a bit higher at 80, and then it's going way higher at 160 millimeters per second. And what we can get from that is a scientific sorting. So from that experiment, I can tell you that the titanium powder is the best one, followed by the aluminum alloy, followed by the scalmalloy. I can sort those powder and discard the powder very easily. So this was the goal. But this interface fluctuation system is very complicated because you need to fill the printer with powder, recoat the powder, take a picture, and then measure the interface fluctuation. So the question is, if we do the test inside the rotating drum, which is a test that takes less than 15 minutes and that only requires 50 millimeters of powder, will I get the same sorting? So here on the left side for the cohesive index, we have the cohesive index versus the rotating speed. And here we even put the recoater speed. So we have a link between the recoater speed and the rotating speed. Now this link is not to be taken too seriously. This is something that is approximative. It will give you a range, an idea on what will be the linear speeds, but it's not 100% accurate. So the rotating speed is the data we should take into account. We are just converting it into the recoater speeds. And here we have the interface fluctuation. And what we noticed is that it was scalmalloy, then aluminum alloy, then the titanium. And here we have the same sorting. So scalmalloy is on top, followed by aluminum alloy, followed by the titanium. And here we can see we are stopping here the experiment at 160 millimeters per second. Now, what you can notice is that the difference between the blue and green line is way higher in the interface fluctuation than in the cohesive index. And the question is why, of course. And why is because the cohesive index inside the rotating drum is only taking into account the powder and the speed. That's it. But the interface fluctuation is a picture that is taking inside the machine. So it's taking everything into account. The powder, the speed, the shape of the recoater, the material of the recoater, the layer thickness, all the process conditions. So this is the interface fluctuation method is way more precise, of course, but you need to fill the printer with powder, which is the goal is not to fill the printer with powder. So we wanted to understand Is this good enough? Is characterizing the powder is enough, or should we also characterize the recoater? Has the recoater a big influence of the powder characterization and on the spreadability characterization more in general? So we did a second set of tests with 4 powder that we can see here, and we get a sorting which is, let's say, relevant with a rigid wiper. And so the question is, are we going to get the same results while using different wipers than a rigid wiper? So this is a bit of a complicated slide, so I will try to go slowly inside this one. So we tried 3 different wiper. One is a wiper V4, which is a double lip one. The second one is a wiper V3, which is a single lip one. And the third one, I don't have a picture, but it's just a rigid wiper, is the one we used before. And the goal was to see if the interface fluctuation was different wiper to wiper. So the question is, does the wiper has a big influence on spreadability? We know the powder has a big influence on spreadability, so we know we must characterize powder in order to predict spreadability. What about the wiper? So we have 3 graphs, one at 30 mm per second, one at 80 mm per second, and one at 160 mm per second. And we can see that at 30 mm per second, the interface fluctuation for the 3 wiper are always in the same range. For the Inconel fine is approximately the same range. We have big error bar here because it's fine. For Inconel it's the same range. For aluminum alloy it's, let's say, the same range. For the Scalm alloy we have a little bit a bigger difference. We can see that the single lip wiper is working better, but it's still approximately the same range. For 80 mm per second, we can see that for the 3 powder on the right, we are also in the same range. But for the powder on the left, the Scalm alloy, we can see that we start to have a big difference depending on the kind of wiper we are using. However, if you use the double lip one or the rigid one, you are getting the same interface fluctuation. So this means that powder characterization is still the first importance in that characterization. And then when we go at 160 mm per second, we can see that the differences are big, and therefore the wiper must be taken into account. So if you want to spread your powder at 30 mm per second or 80 mm per second, you can just use the rotating drum principle to characterize your powder. You will get a good idea on spreadability. You can set up a pass-fail test, and you can compare powder and sort them for more spreadable to less spreadable without having too much issues. This will not be a problem. Now, if you want to recoat at 160 mm per second or faster, then there is other parameter that you must take into account, such as recoater shape, which is the one I'm talking about right now. The recoater shape must be taken into account. So what we thought it's going to do is, because first of all, we are a company, so our goal is to sell equipment. We wanted to understand how we could take the wiper shape into account. But inside the granule drum, there is no way. The granule drum is just there to do powder characterization. So if you want to take the powder shape into account, the only way was to build a test bench with the wiper on it and to spread the powder, which is a very complicated method that requires a lot of room, a lot of time, and that is not as easy, let's say, as the rotating drum principle, where you just pour powder inside the rotating drum and wait 15 minutes and you get all the results. So we turn to one of our partners that may have a solution for us, which is DCS Computing, that are using a code named Light. So Light is a simulation software for granular material. And what we did is that since the geometry of the drum, the granule drum, is so simple, we can do a simulation of the powder inside the software. And what is good is that we can still follow the process condition, because we can take several pictures at 20 RPM, 60 RPM, and then do the same simulation inside the software, and then set up some parameter for the model that will match, let's say, match the interface the best at the speed we want to work to. Because, for example, if you want to calibrate your model with angle of repose, then you do a heap, you get the angle of repose, let's say for 47. You do the set of parameters for your model, you get 47 as well, and then that's it. Your model is calibrated. But you can find several set of parameters that will match this one angle of repose. When it comes to here, the test with the granule drum, since the goal is to match the interface the best as you can, let's say, there is only one set of parameters that will give you a perfect match, and this perfect match may be a perfect match at 20 RPM, but not at 60 RPM. So you need to find a set of parameters that will match, let's say, the best at several speed. So this is a way to prove your model even further, and to really give a model that will behave the same as the powder inside the drum. And since the drum is a proxy to the recoating process, so we have the same process condition, then if you want to do a simulation on spreadability, then you can, and you will get very good results. So this is what we did here. So this is not a webinar about simulation, so I will not spend too much time on this slide. Here you have all the DEM parameter that we choose for the simulation. You have all the setup that we decide to put, and then we run the simulation, and we can see that we can assess spreadability with a simulation. So on the right side, you have the side view. So this is the recoater, this is the heap of powder that we are pushing, and this is the powder that is spread. You can see the scale of color here. And then here on the middle is the top view of the recoating process. So in the yellow is the heap, and on the dark grains are the powder that are spread. And so this is how we can, with the granule drum, calibrate a model, and then use this model for simulation. And in the simulation, you can test all the shape of recoater that you want, because it's only one shape to change. And then you run the simulation again, and you have your data, and you know what will spread well and that will not spread so well. So now I'm already talking for 27 minutes, so I will just give you a brief conclusion. So the conclusion is that cohesion drives spreadability. So the amount of forces that are making the grain stick together will get in the way of spreadability. So if the powder is very sticky, it will not spread well, and it will have high cohesion. If the powder is non-sticky, so it will have low cohesion, and it will spread very well. So this is what I will try to demonstrate to you today in this presentation. Spreadability depends on the recoater speed. Depending on the speed you choose, you will not spread in the same way. And some powder have shear thinning behavior, some powder have shear thickening behavior, and you can assess that with the rotating drum test. And so a good way to assess the optimal speed range for a given material is to run the rotating drum test. With the rotating drum test, you can define at which speed you should recoat this powder, if this powder is going to recoat well or not, or if I'm doing R&D, I can create several batch of new powder and compare them directly in the granule drum to know in advance which one will spread better. So this is the end of my presentation. I will just give you 2 more slides about how we can go further. A topic that was addressed before is binder jetting. And in binder jetting, one of the challenge is to control the binder. So we don't want the binder to go through all the layers, but we don't want we do want the binder to go through the first layer at least. So we need to have a powder bed that is dense but not too dense. And one way to characterize the density of the powder bed will be to the granule pack, which is also one of our instruments that measure the compaction dynamics. So this is the number of taps. We are doing tap density, and we measure the compaction dynamics of the powder. And if we get a powder that will compact very, very slowly, so it's a powder that is very stable and that you can control the density of the powder bed. If the powder is compacting very quickly, so very vertically, then the powder may be too dense because just the vibration of the machine, for example, will make the powder bed compacted. Another way to go further in powder characterization is with tribochargic measurement. So if you want to measure the amount of electrostatic or charges inside your powder, you can with one of our instruments as well, because as you can see on the picture, the powder can stick to the recoater or stick to the walls of the machine. And if the powder is sticking to the recoater, then the recoating process will not be as smooth, which can lead to bad parts as well. So it's very important to understand the charges that are inside the printer. Anyway, this may be topic for other webinars. If you are interested in those topics, do not hesitate to follow us on LinkedIn or to visit our website, www.granitools.com, where you can find all the application notes and all the paper that we publish for free. So you can just go online and you can download them. And if you want more information about our instrument or you are looking for such instrument, you can either contact me directly or ask for a quote on our website, or even view our instrument on our YouTube channel, Granitools TV. So thank you very much for listening to me. And if you have any question, I will be more than glad to answer them.
Thank you, Alex. That was a nice presentation. I think there's a kind of echo. I don't know why. Now it's okay. Good. Yes, this was really a nice presentation. I think now it's time to get some questions. If you want to ask a question, you can raise your hand and I will try to give you the floor to ask your questions, and we can start with the first one from Bruno Vicenzi. So, okay, Bruno, can you unmute yourself? Yeah, hello.
Yes.
Actually,
hello.
Bruno is my colleague in EPMA, but he has a question.
Yeah.
Yes,
Bruno, I think it's not a secret.
Yeah.
I have a question for Klaus, actually, who I see on the screen. About the multi-material production of multi-material parts with additive manufacturing. What is the status at the moment of this kind of technology, and what would be the best technologies as far as you understand now?
Yeah, good question. Multi-material additive is still a challenge in metals. There are some papers being published also by Fraunhofer colleagues who did this with steel and copper, for example. But having a machine in the market is not yet the case. So there's no available system in the market yet. There are some approaches to do multi-material additive with metals. One is the infiltration process of X1 done by binder jetting. So you print a steel-based green part and infiltrate that after debinding, infiltrate that with a bronze or a copper alloy. Then you have a material mix. No shrinkage, by the way, but a material mix. And the other way is simply building two materials upon each other. This is possible with many applications already, but if you really think of mixing materials wherever you want in the part volume, this is not possible yet. This is not state of the art yet.
Thank you.
Thank you.
So our next question is from Manuel Caballero. Manuel, if you hear us, can you unmute yourself and put your question?
Yeah. Well, this is Manuel Caballero from the company Mimecrisa. So we are making metal injection molding, but we are moving to our interest to additive manufacturing. But what all the tests that we have done is with the newcomers or very old-fashioned technologies as binder jetting or filament printing. so that is closer to metal injection molding for prototypes and so on. So my question is to the company Granu Tools. Have you done some tests, or you are thinking in developing tests to know which kind of powder will be optimum for these new technologies as binder jetting or filament? Because right now it's a kind of black box coming from the machine makers.
Okay, so thank you for the question. So for the filament, we don't have a way to characterize it because here at Granu Tools, we focus mostly on powders. Now for binder jetting, we are using our instrument to characterize the metallic powder. So for binder jetting, the Granu drum and the Granu pack are the two we are using the most. And for the plastic printing in binder jetting, we are developing a new instrument, which is the high temperature Granu pack that should be able to characterize the powder in a very, very effective way. So yes, if you want more information about our instrument, you can contact me directly and I can send you, let's say, some more commercial material. But for binder jetting, we would advise you to use the Granu drum and the Granu pack.
Okay, thank you very much.
Welcome.
So may I also comment on that question? With binder jetting, it's always a trade-off between spreadability and sinterability, so sintering activity. And the finer a powder is, the more surface you have, the better or the higher the sintering activity is, but you are limited in the spreadability. So it's a trade-off between spreadability and sinterability, and this has to be developed for each specific material, at least material family. What we've also seen are mixtures of gas atomized and water atomized powders, which have been used successfully by some big users who did these kind of tests. But there is not the metal binder jetting powder yet. It has to be tested for each material now.
Thank you.
Yes, any more questions to our speakers? Well, actually, I have a question to Walid. I see that the packing or the cohesion, all these are, you're able to measure all these type of things. Are there any method to measure humidity in the powders? I mean, either in Granu Tools or in general, speaking in literature, that is there a way to measure the humidity in the powder, or there's a kind of measurement method for that?
So I cannot answer that question because I honestly don't know. I can tell you that there is two things to take into account. First is the humidity of the powder, and secondly is the humidity of the atmosphere. So what we do here in Granu Tools is that we have a humidity conditioner called the Granumidity that can condition the humidity of the instruments and do some measurement at specific humidity. And what we do when we want to condition powder at a specific humidity, we do have a system that we do not sell, but we develop it our own, where it's a rotating cylinder with some air at a specific humidity that will go inside the tube and condition the powder at a specific humidity. Now, in our case, we let this machine run for a long time to make sure that the powder is at the defined humidity, because we do not have in-house a way to measure the humidity of the powder directly.
Okay, thank you. So
it's a very good question. Humidity is a very big topic. Temperature and humidity are very big topics.
It was one of our headaches in the past that if you are not able to define or challenge with humidity, it's a big problem in every steps of powder metallurgy. Either it can damage the powder itself, or it kills the flowability of the powder. So that's why I put on this question?
It can be measured indirectly by the flowability usually. And the amount of water could be measured by Carl-Fisher titration, for example. This gives you quite exact values, but we have seen in our recent experiments that the amount of humidity is so small that it's really tricky to find the right setup to really measure the real amount of humidity. But Carl-Fisher titration is the most method we know so far.
Thank you. So I think we are at the end of our. One more question. Yeah, Mahesh. Yeah. Hello, Mahesh. Do you hear us?
Yeah. Hi. I'm
Hello.
Mahesh Mani. I'm working as a metal scientist in GKN Aerospace, UK. My question is for granular tools. Other than simulation, is there a way to understand the effect of different wipers at different speed? If you want to understand the effect of recoating speed, if you are using a different wiper, if we start to use a new wiper, other than simulation, is there a way to understand the behavior?
Of course, you can build a test bench. So a test bench is a second way to characterize the recoater effect on the powder. And so you are just putting the real recoater on the test bench, and you will assess the powder layer with a software like we are doing it, measuring the interface fluctuation with the software. But once again, this is always the compromise, because you need the test bench to do this kind of measurement, while with the simulation, you let's say just need a computer. So, but yeah, if you want to characterize the recoater, especially in university, they are building lots of test bench like that, which is just basically a recoater, a heap of powder, and then a flat surface, and they are just recoating the powder on the flat surface.
Okay. Thank you.
Well, thank you.
Welcome.
So, are there any more questions? I think we are finished. Oh yeah, I think there is one more question. Huh? I see. Yes, Tommaso, if you can unmute yourself. Yeah. Okay.
Yeah.
Please.
Thank you. I have a question for I don't know, for all the speakers. What is your opinion for the future? Because in the recent year, more or less, I saw that the DD technologies are becoming more and more precise. And I want to know, in your opinion, if in the future will take the lead in comparison to the SLM or other technologies.
I'm sorry, the audio connection was very bad, but I still think that all different AM approaches will make their way into production, depending on the products they are meant for. There is not the one AM technology which is capable of printing and producing all kinds of products, but all the different processes have their pros and cons for specific products. If you look at special bronze materials in large numbers, you might choose binder jetting approaches. If you look at very precise steel-based materials or aluminum-based products, you may choose laser powder bed fusion. And even fused filament fabrication has its market and will have its place for certain products. That's my opinion on that.
Yeah, okay. Thank you very much. I think the same, and I wanted to know your opinion. Thank you.
Well, as Klaus mentioned, the processes themselves are under development still. Actually, I want to mention some view of mine at this point. Maybe you know or not, EPMA is the liaison office between the Technical Committee of Powder Metallurgy and Technical Committee of Additive Manufacturing in ISO. As Klaus mentioned, standardization in AM is a big challenge because, you know, to put a standard, you should have been settled down with all the steps of the process. But in additive manufacturing, the processes themselves are still under development. So it is difficult to answer your question. At this moment, well, what I can say is the application determines the method you will use in additive manufacturing, but day by day things are evolving. For example, binder jetting was just a kind of lab work maybe 5 or 10 years ago. Now it's really a very important step in process in additive manufacturing. Maybe some other methods that are just kind of lab work currently will be one of the most important processes within the next years. We don't know. We will see that all together. So, yeah, questions are coming one after the other. I have another question, I think, yeah.
Again from Mahesh, sorry, I forgot to ask this one. Is there any standard developed for understanding the spreadability, like flowability? That is apparatus for there is Hall apparatus like that. Is there any tool being developed to test and understand the spreadability of a powder?
Well, that's still under discussion. I think Granotools is of one of the subcommittees in TC261. Philippe Franqui, who is the executive director of Granotools, who's not unfortunately in this meeting, he is one of the members in this subgroup. It's 73, I think, or 71, I don't know. Yes, there are strong discussions and a lot of work being done to bring in some standards about flowability, but they are not still 100% clear yet.
Mm-hmm.
Okay.
Yeah. To add maybe one comment on that. The only standard there is on flowability today is on the whole flow meter, and the whole flow meter is not precise enough to characterize metallic powder or to see difference between metallic powders. So this is why Granotools, amongst other companies, are pushing to have a standard for additive manufacturing to be set up as soon as possible.
Okay. Thank you.
Yeah, that's all I think for today. Thanks everyone for joining our webinar. We hope to see you in our next webinar about metal injection molding, which will take place in August. As I said before, you can follow from LinkedIn or our website about EPMA webinars and all other events. So before closing, I think there's one last question. It's from Talha Muslim. Talha, do you hear me?
Yeah, I can hear you. I would like to ask about, like, for complex aerospace components, for example, for DED, when we try to qualify the component and we have to know, like, traceability of the powder. So how do we have traceability, like, when we qualify the powder, when we qualify the final component?
Well, it is an issue, I think, that the powder producers should answer, because now all powder producing companies are putting on the market new products for additive manufacturing especially. So there's a certain lot number with the production date and other details on the data sheets. Mm-hmm. I think the only way to do that is if on the AM machine, if you have a track of the powder supplied, I think you will be able to answer this question. I don't know what you think, Klaus.
It's a question of trust between powder producer and part producer in the end. There are different approaches to settle a kind of powder traceability instrument. At the moment, we still do not know which powder characteristics we have to check for the different processes. So if you look into the standards in aerospace, for example, in Germany, it's a DIN 65120 something. They have put together a list of methods. They test their powders. If you look into the automotive industry, they have put together other standards and other methods. So this is still under development. And at the moment, it's simply a question of trust and appointment between powder producer and part producer. And this works because industry works. If you look into the dental industry, there it works very, very well. They produce thousands of parts every night. And there these appointments have been made. The trust is there, and so it works.
I see.
If I can just maybe add something, because you talk about the aerospace industry, we do have contacts that are testing the powder to make differentiation from batch to batch, and we do find a lot of difference in flowability from batch to batch. So, I mean, on ground tool side, we know that this is one of the big topic of 2020 and probably 2021 for the powder producer to improve the quality of the powder and more having a constant in flowability. So I think in the coming years, when powder producer will sell powder, the datasheet of the powder will be more precise and will comply with different characteristics than just PSD and shape, which are already largely used. Hopefully, when there will be a standard on additive manufacturing, a standard to characterize, for example, spreadability, then they can use this standard to characterize the powder, and so you will get better knowledge of the powder that you are ordering.
Okay, thank you.
Yes, I think now we're closing. Thank you, everyone, for attending our seminar. As I was saying, my last words before the last question. We would like to come together in our next webinar on metal injection molding in August, or maybe the next one about hot isostatic pressing in September. So until then, have a nice day. Thank you very much once again. Bye-bye.
Thank you.
Thank you. Bye-bye.
Bye.